See the title, should be knowledge about what? I didn't put this. Okay. Yes, these are languages, huh? So it's a different.
Yes, but this here is one of the lectures, not the language, this language from the subject.
I'll just ask. Okay, so we're going to proceed with Professor Largas. But he's going to cover some topics. Starting with derivatives and starting with language, which is on the board, continuing with derivatives, and then having importance in our decomposition, which we saw today in the computer lab, in the context of
Good afternoon. Well, due to a variety of circumstances, we are not following exactly the program, so I am going to talk about things which might allow you, students, to read from the original paper or from my free English translation, so that you can advance to a certain point, get enough experience to complete on your own reading. So the first question, the first topic, which was for last time, we probably enjoyed with transmissions. You already know the exterior derivative of the exterior product. But in the first example, we are going to be also the exterior derivative of the original product. And then is going to be also the Canada derivative of the original product and the Canada derivative of the exterior product. Also, there will be the Canada and exterior derivative of the product. As we know, okay, for the language rule for the exterior and for the inner product, then by difference we have the Clifford and exterior derivatives of the product. We shall give only a brief indication as to how one gets this from the definitions and from a few properties. The details, you can get them on your own. For me, it is more important to start giving the flavor of how one operates. And the most important remark, which is nowhere, and I only noticed a few months ago, very few, but I have not computed more. Look at this. One would expect, okay, some kind of high symmetry with respect to U and V. And here, symbols. This symbol is of A, B, C, etc. Okay, with B minus A, minus B, minus C. You gave me the name, the other name, but I forgot, so I don't care about names with permission of Professor Dracula. Okay, moving. I noticed, right, see, this looks very much like that, one understands, okay, the presence of this, because an operator may have to go through U, and then you check the sign. Okay, I'll show this one, I will show all of them. But, as an exercise for you, even when you get interested, okay, my suspicion is that these formulas can be right far more simply, because I found already that this can be done far more simply. Well, I'm going to write that in simple form. What happens? That this one, these are the formulas given by Kepler. Okay? But this one happens to be minus 2 times that. By computing explicitly, one finds that. Therefore, all this would be simply minus eta u. And that looks far more symmetric than this one. Something similar is likely to happen with those formulas. Yes, please.
Are we working on a commutative algebra?
No, the clear algebra is not commutative. Okay? Only the stereo blocks are commutative. If the others are symmetric, I want to be careful. Because when you have the stereo block, say of a 2-4, okay, with a 3-4, then you can type and no. Yeah, whenever one of them is even, okay, the sign of the product is -1. If this is a, okay, if the grade were R and the grade were S, then the grade is, of the product, the factor is -1 to the R times S. Okay? Because each of the S terms here, if this is different from 0, okay, it's because all the vectors are independent. And then when you move these past 2 of them here, you do that. Okay? You are having R changes of sign, and you do that S times. Okay, so the sign that you're going to have is -1 ERS. If R and S are both odd, then the product is odd and you have -1. Okay, so one cannot even say that the stereo product is anti-commutative only for forms, and when they are multi-vectors or differential forms, it depends on what combination you have. Alright, so what would be this? them in different ways. There are so many possibilities that it depends what possibility to use. You are going to get formulas which are more or less complicated. So, what is going to is this one? Here it doesn't matter whether I use dx mu's or omega mu's. Okay? What I'm saying, you can't replace the ones by the others because we are not going to be differentiating or expressing that they are differentiations. Okay, so this is going to be dx mu, or you prefer omega mu. Can derivative still product of v u still v still if equals this product, that will be dx mu still u v plus dx mu dot u v. That's one way of proceeding. Probably this is what he is starting to do. I'll check. Okay.
No convection. The dx mu, no convection. To make it
Thank you. Proceed. Applying the rule, I'm going to have to discuss these problems today, this afternoon, because I didn't have to use my previous system. Okay, but certain operations are going to be there, and that will be the interesting part. Okay, this is one way to go. Is this the way forward? I could reduce these things I know by now going to, okay, I could write this. I don't know whether this is for the plus u dot b. And here I can do something else. If I were facing this, I have to give a rule for the different algebra, which we have not talked about, but it's very interesting. Namely, what is the dot product? Let me write in order to simplify. Since this, the structure is the same, whether I use differential forms or omegas or other letters. Let me assume I have something like more. But I do so with 3 to give an idea of how it works, and you can then use general formula a little bit. Okay, this is A. I haven't proved yet. Dot B, yes, times C minus A point C B plus alternating signs, actually, plus A point B BC. Now, I haven't seen the proof for years, but when proving this, let's put it if what I'm going to do now, I'm going to do it by using numbers at the front, I will get a mess. But, so this is sometimes, you have to prepare Clifford algebra only for little details like that. Now I'm going to prove this. For that, I'm going to develop this, I'm going to develop this, I'm going to develop that, and see that I get this. In doing the proof, I could develop, when I get here, there is no difference. What is A dot B? A dot B is 1/2 of, I forget the 1/2, no, there is 1/2 everywhere. AB plus BA plus BA CB. Now the next one, with the minus sign, I would say, this is AC plus CA followed by BD. And you're not going to go anywhere. It is a mess of terms, you know, one doesn't recognize. However, in group, AB plus AC, if I put here AC, next term, minus B, AC, D, minus B, CA, D. Notice it starts to repeat itself.
The brackets there. It is A, B, C, D. What is the meaning of this?
I don't hear you. What do you have?
Even the brackets, this A, B, C, D. How do I evaluate this?
Okay, AC is a dot product. It is equal to AC plus CA.
No, you have written A, B, C, D. Are there dots down there?
Yes, the dots.
I don't see them.
Oh, the dots have disappeared because I have replaced the dots. Next one.
I see.
Next one. This is a number. I put it at the very end. I put it wherever I want. And what is this? AD, BCAD, I put this here. BCAD plus BCDA. Hence, remember, these are those 3 lines. I added the 3 lines. A, B, C, D plus B, C, D, A. 1/2 of that. So, this equals and what is this? This is precisely that. Okay, I've developed like that. Apparently, I want to prove this. I have developed this, I have developed that, I have developed that. It is there, I have added all of it, and I reach this. And what is this? I put it as 1/2 A plus A. And this one, A is of grade 3, takes this form. So I have proved that the sum goes away is equal to V. Now, this works not only for the trivial products, but also for stereo products. Because it has the advantage, it happens that when you multiply and trivial multiply, you are going to have grades from R plus S to R minus S, assuming R is R minus S in absolute value. If, the formula then is going to become is going to become, I have to not lose any term, okay? Take here, because if it were in that way, okay, if it were in that way, then this has to be a grade 2. Because it is a dot product, and that a contraction, a vector is a trivector. So the dot product is going to be a bivector. If I did not have, if I had anything else in here, okay, then the grade would not be 2. So just, you can think about it, what's I've done the previous formula. So, if I have the dot product by an exterior product, okay, the same rule works. Yes, please.
It would be another way to prove that a matrix you can decompose the antisymmetrical part and the symmetrical part.
Well,
it is another way to prove it.
Yes, I mean, I remember proving, okay, first taking this, developing this and developing that. I'll see whether I remember an alternative way to this thing, because I think I remember. Look, if I do this, maybe I continue, this is necessary, but here is, you can always look at it. Either this or in some notes. But what is, I'm going to give you the trick, so to speak, so that you and we are treated in a more symmetrical way. The trick in the form. We know it from, the calculi and the suburbs. Namely, and then we first leave the second term constant, then we leave the first term constant. And before doing the actual operations, we transpose it. See? So it is more important for me to do now things with the trick than otherwise. But I have not even prepared this for me. This is what we do when we partial differentiate. We say this is going to be partial the same partial differentiate. U, V constant plus so the trick is now, instead of going by brute force, before doing this operation, I change the order. I change the order to follow whatever rule applies. Do I make myself understood?
What means V constant?
That I will know when differentiating, I have CP2. Okay, before doing this, going to differentiate this and treat this as if it were a constant.
Yeah, but you differentiate in some direction.
So
You differentiate in some direction of.
for the moment, I don't have.
No direction.
Right.
I forgot the meaning of this function.
Okay, thank you. I was going to leave that for later on because I was going to start at the computer. This element was
This was.
okay? Now, with regard to this, if you were going to read the calculus, then you would have to use the expression as for that. I don't like to remember formulas, except the equations of structure. And remember that I did the other day, I use orthogonal bases because they are canonical when we have metric. So, I said that the omega mu, I express everything as a linear combination of products of the omega mu's. The omega mu is omega mu exterior omega mu equals omega mu have enough? Now, I could use find my, okay? This, on the other hand, is omega nu, stereo product, the dH I want, the d nu I want to obtain. This is the differential by going by the Taylor calculus, okay? And this is the differential going by the equations of structure. I want both to coincide. So I could identify, say, here this is going to be, by comparison, the omega nu u, the covariant derivative of the u. But I could also say, okay, first write this as omega lambda, okay? Omega lambda stereo minus omega nu gamma, gamma nu, and say, this is contracted with this, okay, this index goes with that one. This index is because it is here. This index.
There is this in an index, I wasn't very convinced. In the last row, it's missing an index. It's new where is new.
In the last row, on the right.
On the left.
Yeah. You mean this term?
Yes. It's the mu.
Oh, thank you. Yeah, I want here to thank you.
Okay.
Thank you very much. Trivial error. Okay. So, okay, this is the usual formula for the u, and here with the u, and we have the place we are doing this one, and we'll use it for an arbitrary u later on. Okay? So, if I look at this equation, okay, before I write it, I'm going to write wrong. Because some people wake up when you write something that is wrong on the board. So, wrong that d mu of omega mu is equal gamma mu. Here I have mu lambda. lambda, omega lambda. Is it wrong? It looks right. It looks right, but it's wrong. And well, first you don't obtain the formula typical for the divergence, and you only have current divergence, so to speak. And you can say, aha, I could do this, but I could also do that, and both are right. No. Because what happens is that the term which is going to appear with an opposite sign on both equations is not tensorial. Therefore, the two equations. Okay, so the right thing is this. So here it says therefore that d lambda of omega nu equals minus omega nu gamma nu lambda. If for comparison with this, I replace the lambda with nu and the nu with something else. Okay? So I start by replacing this nu, which is newt, by something else, and now I replace the lambda with nu for comparison with that. So, and we are comparing this with this. Here, let me put here. Let me check this. Nu, sigma, and this is sigma.
It's okay, no problem.
Okay, with this one, the order of this two doesn't matter because this is a function, a zero form. Okay, and for comparison, I'm going to put here sigma. And notice, if I use, okay, so I have to use this one and not that one. Right. Now, everyone, assume that I have done this with coordinate basis. When the bases are coordinate, we have symmetry under these two indices. So this animal would be, I will exchange indices, and I will get this expression, and this expression will be the opposite of each other. And one of the two, or both of them, has to be wrong. Okay? Because the difference between these two is going to be twice this one, but this is not tensorial. Because the symbols, what are they called? Christoffel symbols are not tensorial. All right. Yeah, that was reminding you of how one gets the covariant derivative of the omegas. The next step would be, if I have something more complicated, then the Leibniz rule is applied. Example, let me go to the next one. A nu is a nu. If I know that, then I can do any. Because the idea would be, if I had a product of Shankarana's, I apply the distributive property. And before differentiating this one, I will always move into the first place. Okay, so what is this? DSH, I can point the others where it was. DSH. Nu. Omega nu. Sub of H. And what is this? This is, I don't know why I did not to this side. And nu. This is the covariant derivative. We said that it follows the original Leibniz rule without alternating symbols. The alternating symbols appear in the developing process when we deal with exterior products. So, this is going to be NUH. Now I'm going to do the bar. If I am using coordinate basis, this would be partial of NU. I mean, we use another letter in order to define in Greek. What would that be? Partial of NU with respect to X nu. If I were dealing with coordinate basis, if we are not dealing with coordinate basis, the differential of F is, we know, F comma nu, dx nu, but we can also write it as F bar mu omega mu, where those are defined precisely by this, because it is the basis. So we can use it like this, because we know what it is. So, I use that notation then, and I have this is the covariant derivative of this times mu plus mu, the covariant derivative of omega mu h, of omega mu mu.
No, there is, oh, I did change.
Yes, right. Thank you. Omega mu, omega mu.
No, eta. Eta. Eta.
Oh, eta. Thank you. But I have another problem. Here I have eta, so I have to have here eta. Thank you very much. So, and this one is over here, so the rest there it is. Okay, what happens if I would do more if I were less tired, but I would do at the final point actually. So what happens if I have then the Keller derivative, the stereo derivative of a Clifford product, or a stereo product, or a Clifford product, or whatever? I will apply or this is okay. What if I have this one? We know. I realize because I said this is trivial. We know what it is. So it would be okay. We know it would be dx nu. Then comparison with the mu, the notation I have been using for Sorry for those changes of notation, but I apologize. But I do know things have changed in the last days, and I'm not very ready. Okay. Now I will do, okay, D, mu. Now I need to okay. What a disaster, I apologize. I'm going to use a mu here, so I will use pi here. And A is a pi mu lambda. I have this, that is this. And now I will have here d mu of all that, and this would be dx mu. First term, it would be a pi mu lambda, a pi mu lambda, slash, or slash not common, because I'm using Cartesian coordinates. Mu, the omegas, plus, the next term is easy, a pi mu lambda, because I am dealing now with the first term. And the first term is going to be minus some gammas, omegas, and continue with the omegas. Next term, that is squared. Next term will be that I differentiate, I have to differentiate mu lambda, etc. Before, the next term will be plus, again this, a pi mu lambda. Now what I will do is to move this to the first place, and in this case, for instance, I can do it by a simplified permutation. So instead of writing it that way, I will write it, and now d mu, okay, of omega nu, and instead of this is equivalent to alternating signs. In this case, I need to here and nothing else happens. And so on. So you can use all those tricks. And continue now. I have applied the formula here, and in my notes, I developed the formula. But in actual practice, I don't like to remember formulas, therefore I do this. Okay? Simply remember this. Okay, I change subject O. I will continue this and get lost. So, what I'm going to do is, remember I said, in order to solve this, one way in which I could do this is say as well. This is one way dx mu, the mu of that, yes, plus dot mu of that. Or, instead of going this way, I could go, of between the exterior and the dot, I could go simply dx mu. Exterior u, exterior v, plus what? Nothing. This is simply let me take one more step. So you see, I have several alternatives and probably Keller doesn't use any of those, but it's still another one. Okay, let me see what he does. It is confusing because he is not very clear about this. Where is since he has many formulas, I have fewer formulas in when Ramon. Now,
Daniel and Ramon are going to pay the resident.
Okay. So, probably tomorrow after resting and writing this down, I'll take some time to develop in different ways one of those. Okay? But, yeah. Because if I continue now, you know what, my mind is too tired to be able to operate. I made all sorts of silly mistakes, which are not conceptual mistakes.
There are too many indices.
Yes. Okay. Some of the things they have better. Does anybody know how to operate this one? No. Okay, I'll go there to some other thing of interest, which is, I'm going to talk about eigenfunctions and spinors I'm going to connect with the Dirac equation. The Dirac equation is this. The Dirac equation is this. Input, output. For the electromagnetic coupling, that would be mass up to constants, in particular the imaginary, that would be m plus En. Where this is the electromagnetic potential of the differential form. The interesting thing is that of particular interest is the solution of U corresponds to a constant when the U, the solutions for U are solutions with time translation symmetry and rotation symmetry. They are connected, time translation with energy, the rest mass of the electron, and rotational symmetry, the speed of the electron. In the Kerr calculus, energy and speed, energy and okay, it becomes angular momentum and charge. Energy, momentum, and chirality come together. What happens? Why? Was there a question? Do you have the James not doing that? No, no. This is very interesting because what happens? In general, here are going to depend on dt, on dx, on dy, on dz, or other conditions, or other coordinates, but and also on t, x, y, z. In regular quantum mechanics, we don't use differential forms. Since we don't use differential forms, this doesn't appear. What happens if we have time translation series? That the dependence on dt has to be of this particular form. And the dependence on time has to be as in quantum mechanics. Maybe I'm wrong in the sign here and there. It's probably better than I do. Okay. If there is an error, you correct. Okay. Now, in addition to properly define, proper value of energy because of time translation symmetry, we may have proper value of angular momentum, which is variant as a simple isolated particle in its spin. And therefore, as part of U, I am going to have 1 plus minus I, not define. This is the plane of the define. This is an idempotent. The square of this is -1. The square of this times that is +1. This is an idempotent. You know what idempotents are, right? An idempotent is something that multiplied by itself gives itself. So what happens with this? First of all, one formula. 1 times 1 is 1, plus minus, idea. Well, let me take just 1 and 1 there in order not to write so many. That would give then 1 plus idea 1 plus I. What did I write? Why did I write 2? I wanted to write this and this. Okay, I have this times that plus this times that plus the product of those two. 2i is minus 1 minus 9 dt dx dy. Did I? Oh, I know. I wanted to take the square of 1 of them. So this is this. Okay? Here we don't recognize that this is an idempotent, but if this is an idempotent, this is an idempotent multiplied by itself, it is going to be the product of two idempotents and idempotents. Now, let me show that this is an idempotent. I'll have 1/4, 1 plus square of this, which will be minus b. No, the square of it will be 1, because I squared minus 1, dt squared minus 1. Oh, and together, the signature is +2. Otherwise, things do not come out right. So, I was obtaining the square of this and showing that this is an idempotent. So, I got the square of this plus the square of that, which is 1 plus 2i dt. Hence, I have a 2 plus 2i dt. I get the 2 as a factor. 2 over 4 is 1/2 equal 1/2 of 1 plus I dt. So it is an idempotent. This one also is an idempotent. Other idempotents, what happens is that these idempotents are so-called primitive. What does it mean? If I were to say, what if I also have translational symmetry? Okay? I also have, I should say, what? A primitive. Do you have a concept of primitive idempotent? No? Okay. suppose that A is an idempotent. And B is an idempotent. Rather, maybe I should, since I have to invent at each point I don't know what is the better approach. Assume that A is an idempotent and B is an idempotent. So, let me write this in the best way. This is an idempotent. If I multiply by another idempotent, this is still an idempotent. So I can create more and more idempotents. For instance, very important, as I said, these animals were going to be fed on no plant. But here is the important thing. When I have symmetries, now I still have not put the dependence on y and z and y and z. So this is going now, the equation of the electron, this is a great advance already, is going to depend on, instead of y and z, I would put rho and z, and I would put d rho and dz. In general, our classic conception of physics this doesn't matter much, because it is said that the electron is a point. But look in the internet for other meaning. And look especially for an interview. Who is Carver Mead? Carver Mead is one of probably the main pioneer of microelectronics. Okay? And he has ideas very opposite to those in the, contrary to those in the paradigm. He says the electron and the neutron, he mentioned the two specifically, he has mentioned also the proton. We don't claim that neutron and proton are point particles. Hence, it is especially the electron is particularly interesting because it is said that it is a point particle, although not everybody says. He says, in my lab, I see that the electron is not a point particle, that it is an extended particle. So, in a case like this would be needed for an electron because it has proper mass and speed and giving carrier. Okay? So this will be used, and I have been using it in my work on superconductivity related phenomena for the shape of the electron. So the problem of dependence on the is going to be notoriously simplified. Okay, what are we going to talk about primitive idempotents. A and B are going to be two idempotents. Is B then will be an idempotent. It will be called primitive if, help me dictionary for my mind is, it is going to be primitive if AB commutes, A commutes con B, right?
If a commute is also idempotent, but sum of two idempotent is said to be primitive, it is not sum of two other idempotents. If it is not,
okay, AB could be an idempotent.
no. Idempotent is primitive if it is not sum of two other idempotents.
Okay, so it's primitive if it is not the sum of two. Isn't there another condition which is whether they commute or not? So it is not
If
And you forgot that.
If you know that, product of idempotent is idempotent if they commute. The sum of two idempotents is idempotent.
Idempotent if they commute. Okay.
But
Why
there is
yes,
no notion. Primitive is about sum, not
yes,
product.
if this cannot be written as the sum, thank you, C plus C minus. I put plus and minus because normally they come in pairs. Anyway, I'll do it with an example. Suppose that I want to have, in addition to type calculation symmetry, I would like to have and rotational symmetry, I would have to have space translation symmetry. So in the same way as for time translation symmetry, we have this factor. We would like to do a half, 1 plus IDT times 1 half, and 1 plus IDXDY, and then I will say, I'm going to do the same for Z. Not IDT, because DC squared is 1. What happens with this animal? This it commutes with this one. It doesn't commute with that one. I can commute these two. Why is that important that they commute? Because of the following. Okay, so observation. Up to this, these two factors commute. This one does not commute, or we know that, although it commutes through this. Why is this important? The unit, I can decompose the unit as epsilon plus epsilon minus, where this is 1/2, 1 minus IDT. I don't go into why the minus is plus 1/2, 1 plus IDT. Now, I can go further and say, this multiplies the unit, and this multiplies the unit. So now I can replace the unit with, if I call these two tau plus and tau minus, I can replace the unit here with this is epsilon plus, this is epsilon minus. So I have 4 terms. When I distribute the product, I have 4 terms. And Keller assigns them because of how things happen when he operates with samples. This would be positron with, let me call it positive chirality. This would be positron with, say, negative chirality. This would be electron with positron chirality and electron with negative chirality. Not yet, because I don't have the wave function. Since this is the unit, remember the sum of those two is the unit. The sum of those two is the unit. Since this is the unit, now I can multiply this equation by, say, the solution of a Keller equation. And put u at the very front. Plus tau plus u epsilon plus tau minus plus u epsilon minus tau plus u epsilon minus tau. What happens? These eigenvectors are constant eigenvectors. They satisfy the property that the scalar derivative of epsilon and the scalar derivative of the epsilons, the scalar derivative of the tau, and the scalar derivative of the epsilons tau are zero. So, if I apply the scalar derivative of u, I can write this as the scalar derivative of u times this plus the scalar derivative of u times that plus the scalar derivative of u times this plus the scalar derivative of u times that. Now, that is because they are constant eigenvectors. But still more, in the subspace of dt, 1 dt, and dx dy, and they play the role. Yeah. Okay. They form a basis. Those four play the role of a basis, and I can in principle write u as u plus epsilon plus u plus minus epsilon plus epsilon plus tau plus u plus minus epsilon plus tau minus plus u minus plus epsilon minus u plus u, and I do not know what those are. But if I now multiply on the right by any of those, what is going to happen? They annul each other. The epsilons, like the tau, satisfy that epsilon plus epsilon minus equals 0, epsilon plus epsilon minus equals epsilon plus equals 0. Same thing with the taus. This is what. Correct me as we knew this, you know this, by times tau minus equals 0. Times tau minus equals 0 equals tau minus. So they mutually annul. And this, the product, those four products, one of them, okay, three of them are 0. And the other one is, I can call them, this one multiplied by, for example, 7. So what happens if I now take this decomposition and multiply on the right, say by this one? When I multiply everything on the right, plus. If I multiply on the right by epsilon plus tau plus, this survive and all the rest are hid. Because epsilon multiply epsilon plus tau minus with epsilon plus tau plus gives 0. Hence, I didn't know what this is. I did not know what this is, but if those commute, okay, if the four idempotents commute, then when I multiply here by epsilon plus tau not plus, if I move this over here because it commutes epsilon plus gives me epsilon plus, and then I have tau minus tau plus, that is 0. So what happens is, then when I multiply that by this survives because times again square, but it is an idempotent. So this allows me to obtain, okay, those U's in this expansion. Okay, this doesn't tell me much, it is true, but it is convenient simply for that. Hence, I know these coefficients, if I know U. And I know that if I have, and if this was my starting point, remember the Keller equation. If I multiply under white, pardon me, if I multiply U under white, say some plus, epsilon plus, tau plus, if that is going to be this in turn is going to be and because of associativity, and we said that this is going to be n positron, positive priority. It satisfies if we have this, then we have that this satisfies the same equation. So from an equation that was not Spinorian, we are obtaining Spinorian equations because these animals are members of the ideas defined by those idempotents. So the Dirac equation in the Keller calculus is a derived, the Dirac equation is a derived equation from the original equation, which may contain electron positrons, or be simply electromagnetic field, or be simply electromagnetic field, or something else. Now, you are going to say, okay, but here there is room only, there is very little room. How we are going to talk about. There is very little room. You have only talked about electrons, positrons. What about everything else? Okay? Well, let's go for a moment to rotations. Rotation No. If assume that I, for what is the square? 1. Hence, this calculates the role of the unit imaginary. Do I make myself understood? So these figures, okay, why do I think in these terms? Because you have probably studied the rotations of the spheres, and you have an exponential here. I am saying you what you knew in your process, not what I did this morning. Okay? Then you have here a 1/2 dr, the minus I. No? You haven't seen that?
Finish.
Hmm?
Write everything.
If I have a member of the algebra, then I said this morning for a rotation, I had A1, A2, the amplified, and here to the right minus 1/2, A1 plus 1/2, A1, A2, 5. Now, when you have, here we have this field. In your course in relativistic quantum mechanics, did you have rotation of spheres, something of this type, but not with A1, A2, but e to the minus 1/2 I, 5, is that familiar or not? But we have seen here that the unit imaginary we saw this morning in rotations, the role was played in the plane XY was played by the plane. Remember that? Okay, so I said, see, this is also associated with rotational symmetry. Okay, it is natural to at least assume and see what happens that I replace this by the unit imaginary by A1, yeah, 1 plus A1, A2, dx, dy. And that is very important. So this game we can play with the taus, now instead of having here 1, instead of giving them, this is telling me to what does this belong? This belongs to the product of two Clifford algebras. The algebra of the Clifford algebra, what we have called the Kern algebra, and here a tangent Clifford algebra. So we have the tensor product of two Clifford algebras. Remember we said the problem we had for epsilon, instead of having 1 plus I dt, we could have E0 dt. Because the square of E0, okay, with the method I said the signature plus 2, which was minus plus. This also has square plus 1, and this is an antipode. But we now have the richness that, in addition to this, we could have plus minus, okay, we should do this, Aj dxi dxj, with for the three combinations 1, 2, 2, 3, and 3, 1. Now, special situation. Remember, DC. We had a problem that 1 plus IDT and 1 plus IDC mean 1 and 1 plus DC. The problem is that these idempotents do not commute. Maybe I haven't insisted enough in the relevance of the commutativity property. I don't remember whether I insisted on that. I think I did when I had epsilon plus tau plus, epsilon plus tau minus. If these two commute, it allows me to move this over here. So commutativity is very important for the surface. Now, these do not commute dt and dc. But if instead of the I, with this game, I am going to go, now I'm going to have 3 idempotent factors, which commute not exactly this one here. E0. No, E0, and here I have E3. Yes. dt and dc do not commute, but E0, E3 do not commute either. But the products commute. So now I can go and develop this time again further. So look at the amount of possibilities I have for particle reactions. Particles in this game are going to be represented by a spinor solution, of which now we not only are going to have epsilon plus minus, not only tau plus minus, and epsilon plus minus 4, RYT star following Keller in order to mean that I am not correlating them. Okay, so this is going to be epsilon plus minus tau plus minus and also epsilon plus minus and tau minus plus. So, if I have these, if the coefficients are adequate, and I have epsilon plus tau plus epsilon, let me write minus because it has application. Epsilon minus tau minus. The sum with the appropriate coefficients, okay? Then with the appropriate coefficients, the coefficients were complicated because they were functions of rho, theta, d rho, d theta. But in the context of the interpretation of the electron by Carter Beach, okay, these are flexible. And I go to the idea of Carter Beach immediately. Carter Beach maintains that if I have an electron in a box, the electron is going to try to occupy the box as if it were a gas. Okay? He is not just any regular physicist. He won the MIT Emerson Prize for innovation and okay? He's a big guy. He has founded many companies, okay, having to do with more technology, vision. He's one of the pioneers, perhaps the main pioneer of microelectronics. So he maintains then that the electron adapts to the container. Container inverted commas. If I have a proton and the electron attaches to it to form a hydrogen atom, together form, okay, it is as if the positron were the container of the electron. In reality, it is the electron the container of the two. So the electron is going to be to take a certain form, okay, around. Now it is not a probability. We are not dealing here with a probabilistic interpretation because when I have so many ideas that I'm not going in order. And say, suppose I have this sum. What is this? Epsilon minus factor, common factor of epsilon plus epsilon minus factor of tau plus tau minus. But that is one. So where I have here spin-off solutions defined by those idempotencies, now I have just spin-off solutions defined by this idempotent. So I could have I have said that this is somewhat incorrect. Plus epsilon plus minus plus minus plus minus minus. Okay, I have multiplied that by u on the left. Okay, it doesn't make automatically each of those four terms the two options for electron and positors with the two chiralities. What means, however, is that if the factors of those come out to be all right, we may have electrons, we may have positrons, if the factors come out to be all right. For instance, you could have this if you don't have enough energy, you cannot go to create electrons and positrons. Okay, for that, let's look at tau plus, epsilon minus, tau minus, that will represent the pair. Okay? And I'll be working with that. It is part way now, it is posted in the website, but I have to stop at a certain point because all this is research and evolves very slowly. So, then I could leave it as it is and use the one here to create this. Now, if I have the m minus now plus, I could leave this term like it is, this term like it is, and decompose this further with some other idempotent for example, translational symmetry. Translational symmetry is a funny one, because you cannot have going from 0 to infinity. If it is going to be homogeneous, you are going to get 0 density and density. So since I am going to give a picture, something very interesting, I put it in the website that this is incompatible, which quantum mechanics from Keller, with Copenhagen interpretation. Not but this is not quite true. What is incompatible is with the tenet of the Copenhagen interpretation that the wave function is an amplitude probability amplitude. Why? Keller is going to consider a solution, is going to write a solution to u as u epsilon plus u epsilon minus. And I have talked about this today, and with tomorrow I hope I can sleep well to be more alert than today. Then we are going to call this factor, remember, I could compute this. I could compute, and I had this. I did it in a more general case. I have this. So now I will use the formula for the current that on which I have not talked today and talked tomorrow. Okay? And I am going to obtain a conservation law, which looks, we are giving the details only the formula. partial of something with respect to rho plus something which in the language of the vector calculus reads like la divergencia de divergence. I apologize. Partial of rho plus with respect to t plus divergence of j plus partial of rho minus with respect to t plus divergence of j minus equals 0. This is very important because it is telling me that the conservation law, O and rho plus is never negative, rho minus is never positive. So the interpretation for this is that this U plus is made of this, and this is made of that. And the details of this are coming here tomorrow. They are there in the Keller paper. So this is like if charge. The interpretation then of the U of the wave function is not of a probability dense amplitude, but of charge amplitude. It is inconsistent with the common, with having the common Hagen interpretation as a basic tenet. Okay, in that it has to involve some quantity which can take positive and negative values. Therefore, it can be a probability amplitude. Is that clear? So this is amazing. Physicists should be looking at this. Of course, if, because this is possible, that comes to be 0, now the probability amplitude of quantization. Now quantization, what is quantization in this theory? Nothing odd, simply that these DSP-oriented solutions have the proper form. Charge is automatically quantized. When you have something with the appropriate factor properties, or we spoke about, and multiply, say, the epsilon minus plus. If this is the appropriate factor, the phase factor, not only for energy but also for angular momentum for speed, okay, you can have there then electrons, but you need, as I said, those two factors. If the dependence on T and of phi are not the right ones, you don't have electrons. But if the dependence is appropriate, this factor over here, which we said depends on Z, rho, d rho, and dz, that is going to be the shape that the electron takes, either in a box, or in the hydrogen atom, or in whatever. And this comes from Garber-Mead. I'm not making it up. But what I'm saying is, Garber-Mead has said this. I have these mathematics from them. Okay, if I put both together, this is what happens. Keller did not discuss, okay, the implications of this for the, okay, for the interpretation. And now, as I said, we can have solutions in this idea, in that idea, in this idea, in a mixture of S plus with the idea epsilon minus plus epsilon minus or minus, and with all those additional idempotencies that I created when I geometrize I by replacing it with E1, E2, E2, E3, E3, E1, etc., etc. So this is a tremendous opportunity for research, but I found opportunities everywhere that I have done for everything. So some questions, And tomorrow I have some mathematics that complements this, starting with E derivatives as per Keller in 1960. For me, it was a revelation. Okay, questions? Because I think you must be very bored there after I've spoken for so long. Questions?
We should thank you.
All right, thank you. Any questions? There are no questions.
Not yet.
All right.
This was very clear and very deep and very...
Yeah, well, I wasn't very clear with the primitive ideas, but as I said.
But it was okay.
Okay. So, let's go then. Tomorrow, yeah, it is going to be important. Let's be hope they wouldn't send the prescription pills for to sleep. Does anybody have prescription pills to sleep? Nobody? No. Okay. Yeah, tomorrow I want to start with something that may offend Professor Acampo and Professor Kosiewicz in the following sense. Tomorrow I am going to adopt a completely different point of view of yours. I am going to start by exploring the fact which we agree, because you have also mentioned that if I have a vector space and the plane are two very different things. Because in a vector space I have a special element and all the bases are equivalent. Somebody may say, no, not the orthonormal basis, but that wouldn't be what we call a vector space, but a Euclidean vector space. So I'm going to compare just a vector space with an affine space, like the table is telling you. Here I am going to have a special point, 0, okay, and then all the frames, so they are going to be. Here, in a affine space, there is no special point. So in order to be able to use this, here I have to choose a point. And there I can attach now a basis of a vector space, okay, and use vector spaces to study a affine space. But I have broken the equivalence of other points. How do I restore the equivalence of other points? By doing the same construction over all points whatsoever. So if I take on the basis here, to each of the points I construct a frame bundle. The basis space is going to be a space-time, and each fiber is going to be constituted by all the bases. And then we're going to set a fiber everywhere. Now, that is if I have, probably we call that symmetric, okay, anyway, I call it Klein geometry. That is if I have a flat geometry or elementary geometry. But if I have an ellipsoid or any other figure, the different points are equivalent. Or then, if I have an egg and I have a tiny piece of the shell, I cannot move it around. It doesn't fit. So then what we have to do is, instead of having the equations of the structure of a affine space, though that is going to constitute a known, if it is integral, that system of equations, we are going to have a affine space. If it is not integral, we are going to have a space which, in small pieces, looks very much like a affine space. But it's not, it's a generalization. And in that idea, okay, I'm going to go all the way to, in the process, encounter the geometrization of classical mechanics, and I'm going to reach the door of quantum mechanics. I cannot come in, because geometry doesn't allow one to it has to come from somewhere else. I have not told everything about I shall do that, except perhaps insinuated in the very last minute. Okay, what an equation. There is not such a thing, in my opinion, as an equation of everything. But, yes please, no? Equation of everything. An equation of everything. But what there could be is, what there could be is an equation which is the same at all points. Okay, but it looks so simple that you may say this cannot be. But fortunately, I resort to authority and tell you, look, an equation like this was already similar to this, very close, was already postulated by Keller in the 1990s. Do you have a question, please?
You have a question. You said Germany cannot do something.
Sorry?
You do not have a question, but you said Germany cannot do something. In my opinion, mathematics is part of Germany.
Mathematics is part of Germany? Yeah, I understand that, and I'm hoping that they can modify the concept of geometry. Okay, redefining. Because when we know geometry, okay, we have Cartan, this is the last.
No, Germany goes much beyond Cartan.
Yes, but Cartan said this, he didn't go in, okay, this then is a matter of words.
Germany suffered a lot because it was taught in school. And this means that Germany got a limited content. I rented a house in Switzerland. The neighbor house had 2 daughters. They were 12 and 13. They asked me what I do. I said, in Germany. Then very proudly said, we already did this.
Okay, I don't want to use names, but I'm saying Cartan is not even with me. Okay, Cartan, the concept of geometry by Cartan, okay, is not sufficient. Keller is kind of approaching it. Okay? Keller is kind of approaching it, but he is not talking in geometric terms. And in addition, he has a tangent boundary which is the tangent boundary which is at odds with differential geometry. Because differential geometry is the theory of derivatives. Maybe you agree with that.
Perhaps.
Okay, well, again, thank you very much.
Question?
Okay.
I thought that was the time for this question.